Inverses of matrices. So this is basically, it's a mixture of sections 2.4 and 2.5. Okay, so basically what we're going to do is try to use like matrix multiplication to give us a way, like a second way of solving systems of linear equations. So let A be a matrix, well, an n by n matrix, so it's a square matrix. So the inverse of A is an n by n matrix, which we write A to the minus 1, like this, such that A times A inverse is equal to A inverse times A, which is equal to the n by n identity matrix. So remember, IN is the n by n identity matrix. And for example, like I3, for example, is just 1, 0, 0, 0, 1, 0, 0, 0, 1. And the point of this, so what's the point of the matrix, or sorry, the inverse of a matrix? It's so that you can solve equations involving matrices. So if we have the equation AX equals B for three matrices AX and B, in some sense, multiplying by the inverse is going to do the same thing as dividing by A to solve for X. So to solve for X, you can multiply by A inverse, and I'll say on the left. Okay, so for matrices, it's important, you can't just start saying multiply things, because remember matrix multiplication is not commutative, so A times B is not the same as B times A. So multiplying an equation on the left is different than multiplying it on the right by something. So what I mean by this is if I take my equation, I multiply both sides of the equation by A inverse on the left, then it kind of allows me to solve for X in some sense. So you should think of multiplying by A inverse is kind of like dividing by the matrix A in some sense. Okay. We'll see some examples where we'll actually solve things in this way, but any questions about this so far? Okay, so let me give you an example to show you how inverses work. example, let's say A is the matrix -2, 4, -3, 7. So I claim that the inverse of A is -7/2, 2, -3/2, 1. Okay. So to check this, what I do is I just multiply the matrices. So let's do A inverse times A and see what it gives us. So -7/2, 2, -3/2, 1 times -2, 4, -3, 7. Okay. So now we have to think back to last week and how we did this matrix multiplication stuff. So to get the entry on the first row, first column, I take the first row of this matrix and kind of multiply it down the first column of this matrix. So -7 times -2 is +7. 2 times -3, I get -6. So that tells me my entry in that first row, first column. First row, second column, I get -14, but then I get +14, right? Because -7 times 4 is -14. 2 times 7 is 14. Okay, so now I get 3 -3, and I get -6 +7. So at the end of the day, you do get the right thing, 1, 0, 0, 1, right? So this is telling me that A inverse times A is equal to I2. And if you go back to this definition of inverse, you've kind of got to check, like the definition I gave you here, to check that something's the inverse, you have to kind of multiply it both ways. But in a minute, we'll see that that's actually not necessary. But just for the sake of this example, let's multiply it the other way. Let's do A times A inverse. So, okay, so 7 minus 6 -4 plus 4. So this position, I get 21/2 minus 21/2. And then I get -6 plus 7. Okay, if you don't follow all of my algebra here, or my arithmetic, I mean, you could easily do this by yourself, right? You just take the hard part of this is just knowing which numbers to multiply to which numbers, right? But yeah, if I want this entry, I take this times this times this, and yeah, I get that. Okay, so what we've shown here is that A times A inverse is I2, so yeah, so this So this proves that this genuinely is the inverse of this matrix, right? Any questions about that? Yeah. That's a good question. Yeah, this inverse just kind of came magically from nowhere. We're going to see kind of in a few minutes how to find this, but for now this is just mysterious. So all we're doing here is checking that this is the inverse. We're not actually finding the inverse. But any other questions? Okay. So here's a fact which will save you some time. So here I did two calculations, right? I checked this and I checked this. Turns out you don't have to do both of them. So this is just a kind of general fact that if you have two matrices, both A and B are n by n matrices, such that A times B is the identity, then B times A is the identity as well. Okay. So basically, if I want to check something is the inverse of something, I just have to multiply them in any order, and it will imply that the other order works as well. So you only need to check if you're given two matrices and asked to check that they're inverses, like you only need to check that you get this, and then the other direction just holds for free. Okay. So I maybe won't go through why this is the case, but yeah, this just saves you time. Yeah. The other one would be like if you reverse them. Yeah, because technically the definition of inverse was like this has to be true and this has to be true. But what I'm saying is if one of them's true, the other one's automatically true. So you just have to check one of them. Yeah. Yeah, yeah, exactly, yeah. And also like in this one, so we did these two different calculations. It turns out we didn't have to do them both. So once we saw this one, we could just be like, okay, it's the inverse. We don't have to do this one as well. But yeah, you're right. If this one didn't come out as the identity, then the other one can't either. So yeah, it's not the inverse. Okay. Let's see how we can use inverses to solve a system of linear equations. Well, actually, yeah. Actually, I'm going to use the same matrix. So let's say I've got a system of linear equations, 2x plus 4y equals 2, negative 3x plus 7y equals 5. Okay. So something we kind of talked about last time is that this system of equations can be rewritten as a single equation involving matrices. So this is the same as the matrix equation, capital A times capital X equals B, capital B, where A is the coefficient matrix -2, 4, -3, 7. X is the matrix containing our variables, little x and little y. And B is the column matrix 2, 5. So kind of remember before I had written, if you have an equation like ax equals b, I can multiply on the left side by the inverse, and I can kind of solve this equation for x. So this is the same as x equals a inverse b. And in this case, luckily, like this is the matrix we were just talking about over there, right? Same matrix as this one. So I know what the inverse is already. Okay, so since I already know what the inverse is, I can just write like x, which is this xy thing, is a inverse b, which is -7/2 to -3/2, 1 times 2, 1, or sorry, 2, 5, right? And so I don't need to do any Gauss-Jordan elimination here. If I know what the inverse is, I can just do this simple multiplication, which will give me -7 plus 10, -3 plus 5, which ends up as 3, 2, right? Is it clear what I'm doing here? I'm just using the fact that we already know the inverse to basically solve for x. And okay, if I did Gauss-Jordan elimination here, it wouldn't take me that long. It'd only be a few steps. But I kind of feel like if you know this is a little bit faster, I think, than Gauss-Jordan elimination. And one kind of cool thing about this is that if I have the same matrix A, if I plug in a different B, so let's say I want this to equal 12 and that to equal 7, right? A different B, then I can still use the same inverse. I just put different numbers here, and that just gives me my answer, no matter what the entries of B are. So yeah, inverses are quite useful for this. However, as was kind of mentioned before, like this, we're talking about what, like, I'm telling you that this is the inverse, but it doesn't tell you how to find the inverse. So we should try to find them too. Yep. No, not necessarily. Yeah, so to find the inverse is a little tricky. Yeah, I'm not quite sure what you mean by x times b here, but okay, yeah. But I guess what this is trying to say is once you have the inverse, you can solve any system of equations really quickly just by doing a simple matrix multiplication. However, as I said, this doesn't tell you how to find the matrix, the inverse. Okay. And also, I should probably say that this method doesn't always work because there doesn't always exist an inverse. So one thing to notice, or to note, not all matrices have inverses. So in some sense, this method is a little bit limited in that sense. And we'll see examples later. So, okay, so let's then move on to finding inverses. Okay. So let's take the same matrix again, and let's imagine we didn't know what the inverse was. So we've got the matrix -2, 4, -3, 7. Okay. And we know what the inverse is, but let's assume we didn't. Like, let's imagine we don't. So here's the method. So the kind of first step is to write down a matrix. So the matrix where I put A on this side and the identity on the other side. So maybe I'll So what I mean by this is I just do -2, 4, -3, 7 with a line, and then 1, 0, 0, 1. Okay. And now we go back to this method that we all love by now. We do Gauss-Jordan elimination. So do Gauss-Jordan okay. And at the end, if you get to a matrix where I've got the identity on the left side and something here, then the matrix you have here is the inverse. Okay. However, if you get to anything else, so if you're not able to make this into the identity, then there is no inverse. Okay. So and that can only happen, it turns out, if you end up with a row of zeros. So if you get a row of zeros, when I say a row of zeros, I mean on the left side. So then you can just say that the inverse does not exist. So this kind of addresses that question of how do you find the inverse. Okay, let's actually do this in an example. Okay, so I'm doing my elimination, my Gauss-Jordan. I don't know, I'm trying to get a 1 up here. There are various things I could try to do, but I think the most obvious looking thing is I just divide by -2 on the top row, right? So I'll take -1/2, row 1. By the way, hopefully this is, if you're not solid on Gauss-Jordan elimination, this is kind of something that can come up tomorrow, so this maybe is some practice. Okay. So I've got my, right, I do -1/2 times the first row. That means I need to multiply everything in that row by -1/2. I think I did that right, I hope. Okay, any suggestions for what I should do next? Yeah. Yeah, and that's just, that's because when you're doing Gauss-Jordan, you want to think column by column, right? So this column, we're trying to get this to look like 1, 0. We've already got the 1, and now we just need to eliminate this -3. And so that's the right suggestion, is to take, basically, once you get a 1 somewhere in a column, you want to use that 1 to annihilate everything else in that column. So yeah, row 2 plus 3, row 1. And when you write this, this means the row I'm changing is row 2. And what I'm doing to it is adding 3 row 1s to it. Okay, so -3, I add 3 1s, I get a 0. 7, I add 3 -2s, I actually get a 1. 0, I add 3 -halves, I get that. And then this one's 1 because that's a 0. Right, and then row 1, I want to add 2 row 2s because I've actually got my 1 in the correct position already. It was just kind of lucky. So on this side, that's what I'm going to end up with. And then okay, so this is how the Gauss-Jordan would work in this case. There'd just be these 3 steps. And we achieved our goal. We got to the identity matrix here, right? So this is I2. And so therefore, the thing on this side has to be the inverse of A, right? And we can see that that matches what we had before, right? So yeah, this is the method for finding the inverse. Okay. So is it clear? So yeah, this is my original matrix. When I get to the end, this is the inverse. As long as you got to the identity here. If I had a row of 0s here, then the inverse does not exist. Okay. Any questions about any of that? Okay, let's do a bigger example. Okay, so I'm going to do a 3 by 3. So 4, -2, 3, 8, -3, 5, 7, -2, 4. So this is my matrix A, and the question is to find A inverse. Okay. So yeah, we're just going to follow those steps that I wrote down before and seem to have erased or covered up. So we start by just writing down our matrix again. But with the identity on the other side. Okay. And then we just do Gauss-Jordan elimination. So lots of things you can do. Like always, in this case, I don't actually see a really amazing thing to do. I mean, I guess I could avoid fractions. Maybe if I switch these rows and then I subtract, basically use this to get these two things to get a 1 or something. But I'm just going to do it I'm just not going to try to be necessarily clever. Let's just see what happens. So so yeah, I'm going to just make fractions here. So 4, -1/2, 3/4, 1/4, 0, 0, and then everything else is the same. Okay, just dividing the first row by 4. Next step, take the second row, subtract 8 times the first to get rid of this 8. Take the third row, so I'm going to do 2 steps at once, and subtract 7 times the first. If you've done a few examples and practiced this, hopefully by now this procedure, hopefully it'll get pretty, I don't know, ingrained in your psyche. Get a 1, subtract from the other ones, get zeros, so on and so forth, right? Okay, so here I've got the same thing on the top. So, okay, next row I've got, so I had a -3. I subtract 8 times -1/2, which is like adding 4. So I get a 1. Something seems wrong about this one. Is that right? 5 minus 8 times 3/4. Oh, no, that's correct, I think. Yeah, so I don't know, it's kind of boring watching me do algebra here, but I think that's right. Okay, so this is all just arithmetic. Yeah, hopefully that's all correct. So luckily in this case we've got a 1 sitting here in the middle already. Any suggestions for what I should do for the next thing? Yeah. Yep, I like that. Right, because the thing to identify here is that my first row is already good. I've already got a 1 in the right place. So I just need to add and subtract stuff from the, so I need to add half the second row to the first, so R1 plus half row 2, R3 minus 3 halves row 2, because that'll get rid of my 3 over 2 here. Okay, so maybe I'll just kind of quickly write this one down. I've got it in my notes here. If anyone's really fast and they can find, if I make a mistake, let me know, but I think this should be good. One thing to always remember, you got to do the same thing, like when I take row 1 and I add half of row 2, you have to do that for the whole row, right? And that's giving me these numbers over here. Okay. So now my first two columns are looking good. What would you like me to do for my next move here? Yeah? Well, oh, that probably is a good idea because you got these quarters just sitting there. Yeah, well, we kind of may as well do that, but well, I guess I'm gonna do it in a very systematic way that's gonna work every time. So perhaps, even though it's really tempting, and if you do this, like on your test or something, it's not wrong. There's nothing wrong with taking row 1 and subtracting row 3. But just, you know, this could be anything here, right? So it's just sort of lucky that these are the same number. I'm just gonna do it in a very systematic way that's gonna work every time. So what I would prefer to do here generally is multiply this fourth row, or this third row by 4. I do see that that seems silly because I could just do that, but yeah, I'm just gonna take that third row and multiply by 4. Because you might not always be so lucky to have the same number in these two spots, right? But that's a good point. So 1, 0, 1/4, 0, 1, -1, 0, 0, 1. 0, -2, 1, 0, 5, -6, 4. Okay, so I'm continuing from there over to here. Okay, now I'm going to eliminate everything. So row 1 minus 1/4, row 3, row 2 plus row 3. So I know what that's going to be, right? Because I'm doing these operations to get the identity. I know it's going to be the identity. Then over here, I've got -2, 2, -1, 3, -5, 4, 5, -6, 4. Okay. So hopefully you can kind of take my word for it on some of these steps, but this is the inverse. If you were doing this, let's say on a test 3 or something, and then you got to the end of the test, you've got time to check your answers, how would you check this? If you want to know for sure this is right. Yeah, exactly. Just go back to your original, right? This, and just in either order, just take A times this, or this times A, it doesn't matter which order. And if you get the identity, then you know you have to be right. So to check, like compute A times A inverse, right? Okay, any questions about that? Okay, so let's do an example where the inverse doesn't exist. Or maybe that's kind of a spoiler. But you could be given this matrix 1, 3, 2, 0, 1, 4, 1, 5, 10. Okay, and we're trying to find the inverse. So we write this on the right side. And I think it's not completely, to me, it's not obvious right now that this isn't going to have an inverse. But let's see what happens. So I'm going to do row 3 minus row 1. Right, because I've already got my 1. I just want to get rid of this. So 1, 3, 2, 1, 0, 0, 0, 1, 4, 0, 1, 0, and then 0 here. That'll make it 2. 5 minus 3, right? 10 minus 2 is 8. Negative 1, 0, 1. Okay, first column's good. We go to the second column. I'm going to use this 1 to annihilate everything else. So row 1 minus 3, row 2. Row 3 minus 2, row 2. So 1, 0, negative 10. 1, minus 3, 0, right, is my first row, I think. But then on the last row, we can see that what happens when I subtract 2 times the second row, I get 0, 0, 0, right, because those disappear. And then I get negative 1, minus 2, 1. And even though we're not, maybe we are done with the Gauss-Jordan, but even if you were doing this and you weren't even finished with solving it, at this point you can just stop. You can just say, I got a row of zeros. It cannot have an inverse. So the inverse does not exist, and that's because I got this row of zeros here. Okay, so if you ever get a row of zeros, then it doesn't exist.